Good morning. The next three sections are completely related to one another. In this first section, what we're going to do is we're going to further graphically explore the first and second derivative and define something called a critical point, which is going to help us later on. In the next section, we will explore something called a local maximum and an absolute maximum, as well as local minimum and absolute minimum. That should be language that is familiar to you from pre-calc. Then finally, we're going to put those two sections together in our ultimate goal, which is to be able to try and find global maxima and global minima in terms of applications. So for example, let's say you are developing a profit function to model how much money a company earns. And you'd like to try to maximize your profit based on the number of items that you produce. So that would be one example. Another example might be, as a scientist, you have a model of a chemical reaction in terms of the amount of stuff you have, and you want to see when the minimum amount of a chemical is present. So that's our ultimate goal. So today we're going to then, again, further explore the first and second derivatives graphically and get a definition that's going to help us later on. So first, as an example then, let's take a function x cubed minus 9x squared minus 48x plus 52. And I'd like you to try and actually graph this using calculus. So let me just model the steps, and then you can give it a shot yourselves, pausing the video. Try to find the first derivative, the second derivative. Develop some sign charts for the first derivative and second derivative. Find out where the first derivative is positive and negative, the second derivative is positive and negative, to show you increasing, decreasing, concave up, concave down, and then put it all together into a picture. So please pause the video and give that a shot. All right, well, hopefully you said the derivative is 3x squared minus 18x minus 48. And I'm going to find out where this guy is positive and where it's negative. In order to do that, I need to figure out where this guy is 0 and not defined, and put those points on a sign chart, and then I can find out the positive, negative stuff. Well, this guy's always defined because it's a parabola, so let's set it equal to 0. This is a little tricky to factor as is, so let me pull a 3 out. And pulling the 3 out, it looks like I have 3 times x minus 8 times x plus 2 equals 0. So it looks like x equals 8 and minus 2 are going to be the 2 points that are on my sign chart. So let me develop the sign chart over here. So we have negative 2, we have 8. If I put in a big positive number, it's going to be positive times positive times positive, so that's positive. If I put in a number between minus 2 and 8, like 0, I get positive, negative, positive. If I put in a number that's less than negative 2, like negative a million, I get positive, negative, negative, or positive. So this tells me that f of x is increasing, decreasing, increasing. Okay, let's check out the second derivative. And I could do it from here. I feel like this is going to be way easier, though. Because I could just do it term by term and get 6x minus 18. Let's set this equal to 0. And I can then add the 18 to both sides and then divide both sides by 6. So we get that x equals 3. So this is the second derivative. Plugging in a big positive number, like a million, this is going to be positive minus 18 is positive. If I plug in negative 1,000, negative minus negative is negative. So this tells me that f of x is concave down and then concave up. So let me try to put all this together in a graph. And in fact, let me invite you to try to do that. Pause the video. Maybe you got this far, maybe you didn't. If you didn't get this far, try to graph that. What I'd like you to do is actually compute the exact values for this. Actually, I'll do that for you. So in other words, if I stick a negative 2 into the original function, via my calculator, I'm going to get minus 2, comma 104, and actually I'm going to move that over. This is not going to be to scale. And you'll get 8, comma, negative 396. Okay, so those are these two values. So try to graph that. All right, hopefully you gave that a shot. Let's see, at 3, I didn't actually compute the y value ahead of time. Oh, I did compute the y value. So let me put that guy in also. I'm going to put that. I'll put that in a minute. Otherwise, I think it'll be a little bit tough to draw. So let's see. I want f of x to be increasing and concave down, then decreasing and still concave down to this 3 value. So 3 was down here. So let me just increasing, concave down, decreasing, concave down. Go to the way in a second. Okay, so let's see. Increasing, concave down, decreasing, still concave down, and it's going to do that until 3, comma, negative 146. Again, where did I get the negative 146? I plugged that back into the original function. Then it's going to be concave up for the rest of the time, and it's going to change from decreasing to increasing over here. All right, so this is putting all of the pieces together. And these particular points have special names that we need to be aware of. So we would say that f of x has a local maximum of 104 at x equals minus 2. So when I say local, again, hopefully you've seen this in pre-calc, but the idea is that when I'm close to this x value, if I looked on either side, I'm a local maximum, close by I'm the highest point. Now, it doesn't mean I'm the highest point, and in fact, if you keep going, this thing is going to blow up to infinity, so that's not the highest point, but locally, or close by, it's a maximum. We can also say that f of x has a local minimum of minus 396 at x equals 8. So that would be this point over here. And then finally, f of x has a point of inflection. Point of inflection at 3, comma, negative 146. So what's a point of inflection? A point of inflection is where my function changes concavity. So at this point, f of x changes concavity. So again, our ultimate goal is to find absolute maxima and minima, or global maxima and minima in the context of an application. At this first step, we're getting a better visual sense of local maxima and minima, and we're getting a sense on how we can graph a function to understand where those points are. All right, so one other thing that I want to talk about today is a bit of vocabulary that we're going to be using that will help us to hunt down these local minima and local maxima. So let me write the definition down. It's going to seem a little bit weird, but it'll make sense once I give you some examples. So definition, critical point is a point P in the domain of f of x where either 1, f prime of p is 0, or f prime of p is not defined. Critical point is a point in the domain of the original function where either the first derivative is 0 or the first derivative is not defined. So let's give some examples of critical points, and we'll see why this thing is important. Well, the absolute value function has a critical point at the corner because the first derivative is not defined. So this would be a critical point. A parabola has a critical point at its vertex. Here, the first derivative is 0, and it's in the domain of the original function. So those would be two examples. And actually, the analogous upside down absolute value and upside down parabola. Each of those guys has a critical point. So why are critical points important? Well, if you think about it, in order for us to have a local maximum or a local minimum, the point has to be a critical point. It's necessary for it to be a critical point because these are the only ways that it can happen. These are the only ways that it can happen. Okay, so these pictures show us that if x equals p is the location of a max or min, let me say local, looks like f of x is a critical point. And I'm not restricting the domain here. We're going to look at points over an interval in the next section. I might need to clean that up just a little bit. So basically, if I want to look for a max or min, what do I need to do? This is giving me the recipe, the map. I could just look for the critical points. And inside those critical points are going to be my local max, local min. So let me draw a picture here. So in other words, if this is the world of possible critical points, maybe a function has 6 different critical points. Inside that world are the local max, local min. So if it's a max min, then it's a critical point. Question, are there any points out here? Pause the video, see if you can come up with a picture showing a function which has a critical point, but it's not a local max min. Well, hopefully you said one possibility would be something like this. So this guy does have a critical point here because the first derivative is not defined there, but it's not a max min. As another example, the cubic function. This happens to be the cube root function. The cubic function also has a critical point here, but it's not a max min there either. But again, that's okay. Our goal is to find the maxima and minima. So first we'll hunt down the critical points and we'll figure out if we're in here or out here. And how do you do that? Well, that's easy. We can just use a sign chart. So if on your sign chart, your first derivative flips from positive to negative or negative to positive, and it's a critical point, then you have a local max min. So we can just check out plus to minus or minus to plus. If on the other hand, we create our sign chart and we get plus plus or minus minus, well then it's not a max min. Okay, so this shows us that if it's a max min, then it's a critical point. This picture also shows us that if it's not a critical point, it's not a max min. It also shows us that if it's a critical point, it doesn't have to be a max min. So a lot of goodies are in there. All right, so let's do one more example with critical points, just finding the critical points. I'm not really interested right now in max min. I just want to see if I can find critical point. So let's say example f of x equals x plus 1 over x. Let's find critical points. All right, so what I need to do is I need to take the derivative of this thing. Since I'm going to take the derivative, let me rewrite it as x to the minus 1. We have 1 minus x to the minus 2. So we need to figure out where this guy is 0 and where this guy is not defined. This type of expression is something that you're going to see a bunch of times in the next couple of sections. So let's talk about how to solve that algebraically in terms of how do we figure out where this is 0 and where it's not defined. Well, this has a negative exponent. When I see a negative exponent, I'm going to call this type of expression a hidden rational expression. This is a hidden rational expression. The reason it's hidden is I don't see any fractions, but they're actually behind the scenes because, again, it's a negative exponent. So what you want to do at this point is rewrite it as a fraction, a rational expression, and then combine, finding the least common denominator. I think I'm missing a square there. And then put them all under that common denominator. So this is the first derivative of this guy, and this is the thing that I'm going to both set equal to 0 and figure out where it's not defined. So the process that I follow is if I have a rational expression first, a lot of times I'll write it like this because it's easier to take the derivative. Another option would have been to combine at the start and then use the quotient rule. If you follow this process, so you take the derivative, then you have to reconnect it into one expression. Because now that I see this here, I can find my critical points. So I need to find where this guy's 0 or where this guy's not defined. Well, it's going to be 0 if x is equal to plus or minus 1. Plugging it into the top, I get 0 over something that's not 0. And then if I plug in a 0 into the bottom, I plug a 0 into the bottom, I can see that that will be not defined there. So again, to get the top, I really solved this equation. That's how I got that. To get the bottom, I solved this equation. So this is where 0, this is where this guy is, the first derivative is 0 or not defined. So question, are the critical points then plus or minus 1 as well as 0? Pause the video, think about that. Well, this guy is not a critical point. Plus or minus 1 are both critical points. Why isn't that a critical point? Well, as part of the definition of a critical point, this guy had to be in the domain of the original function. If we go back up here, 0 is not in the domain, therefore it's not a critical point. So why do we care about this being in the domain? Well, the whole point of the critical points, again, is to find the max and min. If it's not in the domain, it can't be a local max or min. As an example, not this particular function, but let me graph this strange-looking function. So this is f of x. It's an upside-down absolute value. It's got a hole right at the corner. The derivative is not defined right here. So it would have a critical point there. But is that the location of a potential max or min? No, it's not, because nobody's home here. In fact, if this height is 3, and I ask you, well, what is the local maximum there? You can't say it's 3 because nobody's home. You can't say it's 2.999 because you can get closer to 3 than that. Can't say it's 2.99999 either. So this is why we need to have the critical point being in the domain of the original function. Otherwise, wacky stuff like this could happen. All right, so that's all I have to talk about for today. Today we kind of put together the first and second derivative so we could see how we could come up with a graph. We gave some language to some points, namely the local max, the local min, and the point of inflection. And then we talked about this idea of a critical point as a way to help us hunt down the local max and the local min. Thanks for listening, and I will see you next time.